Hello and welcome to this lesson on separation and purification techniques. In today's lesson, we will describe the various processes used for separating mixtures and explain how these separation techniques work. We will also provide examples of these methods in action and develop the ability to suggest suitable separation and purification techniques for given mixtures based on provided information. So far, we have covered the basics of mixtures. We explored what they are and how they differ from pure substances, recognizing that mixtures contain two or more substances physically combined. Building on this foundation, today's lesson will further our chemical understanding by exploring how we can apply different techniques to separate and purify mixtures. We are going to look at 5 different methods of separation or purification. Each method leverages unique physical properties to separate components of mixtures to their constituent parts without altering their chemical identities. First up, filtration. Filtration is the process of separating undissolved solid particles from a liquid or gas by using a porous barrier, typically a filter paper, and is a straightforward and widely used method. It involves passing a mixture through a porous barrier, the filter, that allows only certain components to pass through. The solid particles, known as the residue, are retained by the filter, while the liquid or gas, called the filtrate, passes through. For example, to separate a mixture of sand and water, you would pour the mixture through a piece of filter paper placed in a funnel. The sand particles would be trapped by the filter paper, while the clear water would pass through and be collected in a container. Our second method is crystallisation. Crystallisation is a technique used to separate a dissolved solid from a solution. To do this, you need to heat up the solution until all the solvent boils and most of it evaporates. This leaves behind a small amount of solvent, so now the solution is highly saturated. The saturated solution is then left to cool slowly. Decreasing the temperature causes the solubility of dissolved solids to decrease, meaning it's harder for the solids to dissolve in the solution. Hence, the solids will come out slowly. This can be observed as crystals growing. The crystals can then be collected, typically by filtration, then are washed by distilled water and dried between sheets of filter paper. For example, to obtain salt from salt water, you could heat the salt water to evaporate the water. As the water evaporates, salt crystals will begin to form and can then be collected, leaving salt. 3. Simple distillation. Simple distillation is used to separate mixtures of liquids that have significantly different boiling points, or to separate a solution, liquid, and soluble solid. The mixture is heated until the component with the lower boiling point boils and vaporizes. The vapor rises through the neck of a round-bottomed flask and passes to a condenser, where it cools down, is condensed back into a liquid form, and collected separately. This labeled diagram shows you the process. For example, to separate ethanol from a mixture of ethanol and water, you would heat the mixture. Since ethanol has a lower boiling point than water, 78 degrees Celsius rather than 100, it will vaporize first. The ethanol vapor is then condensed back into liquid ethanol in a condenser and collected. Distillation could also be used to separate water from a solution of salt water. As the mixture is heated, water will evaporate and then condense, and pure water can then be collected. You may be asked to draw a distillation setup in an exam. One key point is to ensure the direction of water flow in the condenser is correct. Cooling water always comes in from the bottom of the flask and out at the top to ensure all of the condenser is cooled down. Furthermore, ensure that the bulb or tip of the thermometer is level with the opening of the condenser. Now let's look at fractional distillation. Fractional distillation is similar to simple distillation, but is used for mixtures where the components have closer boiling points or there are multiple liquids. This method employs a fractionating column. The column is hottest at the bottom and coolest at the top. As the mixture is heated, liquids begin to evaporate. The vapors with low boiling points reach the top of the column and condense and are collected from there, while those with higher boiling points stay lower in the column. For example, in the petroleum industry, crude oil is separated into components like gasoline, diesel, and kerosene using fractional distillation. The crude oil is heated and the various components, each with different boiling points, condense at different heights in the fractionating column. We will revisit this in organic chemistry. Paper chromatography is a simple and quick technique used to separate and identify the components of a mixture. It is particularly effective for separating substances based on their solubility in a chosen solvent. To perform paper chromatography, first draw a line using pencil near the bottom of the chromatography paper. It is important to use pencil as ink would dissolve into the solvent and run alongside the samples. Then, a spot of the mixture is applied on the line. This paper is then placed in a container with a solvent, ensuring that the pencil line is above the solvent level. This is so the solvent doesn't just wash the sample spot into the solvent container. The solvent moves up the paper by capillary action, carrying the mixture with it. Different components travel at different rates depending on their solubility and interaction with the paper, leading to the separation of the mixture into distinct spots. Substances with the highest solubility in that specific sample will travel the farthest. The produced result is called a chromatogram and can be analyzed with comparison to lab data to identify the components of the mixture. For example, in ink analysis, a sample of ink, which may contain several different dyes, is applied to chromatography paper. As the solvent moves up the paper, the different dyes separate based on their solubility, revealing the composition of the ink. As the solvent moves up the paper, the different dyes separate based on their solubility. This reveals the composition of the ink. Each separation technique has its unique applications and is chosen based on the properties of the components in the mixture. For example, filtration is best for separating a solid from a liquid. Crystallization is ideal for obtaining a pure solid from its solution. Simple distillation separates liquids with different boiling points. Fractional distillation handles mixtures with closer boiling points, and paper chromatography separates and identifies the components of complex mixtures based on solubility differences. Understanding these methods allows us to analyze and purify substances effectively, whether in a laboratory or industrial setting. In today's lesson, we delved into the physical processes used to separate mixtures, emphasizing that these methods rely on physical properties without altering the chemical identities of the substances involved. We discussed 5 main techniques: filtration, crystallization, simple distillation, fractional distillation, and chromatography. We began by discussing filtration, a method that uses a porous barrier to separate undissolved solids from liquids or gases. We then explored crystallization, which separates dissolved solids from a solvent by allowing the solvent to evaporate, forming solid crystals. Next, we covered simple distillation, a technique for separating liquids with significantly different boiling points by heating the mixture and condensing the vapor of the lower boiling point component. We also examined fractional distillation, which extends simple distillation by using a fractionating column to separate liquids with similar boiling points through repeated condensation and vaporization. Lastly, we learned about paper chromatography, a method that separates and identifies components of a mixture based on their solubility in a chosen solvent. Each of these techniques is chosen based on the specific properties of the components in the mixture, allowing us to effectively analyze and purify substances in various contexts.